Hello everyone, today in this video we'll be discussing the fifth module of DSA. So we have three main topics here. The first one is hashing, second is priority queues, and the third one is optimal binary search trees. So let's discuss each one by one and make sure you watch this video till the end. Easily you can score more than 80% marks. And please do like and subscribe. It helps me make more videos like this. Without wasting more time, let's get started. The first topic is hashing. Okay, we'll discuss what is static and dynamic hashing. So before that, let's discuss what is hashing. Hashing is the technique for mapping keys to values. Okay, and for that hash function is used. And hash table stores and retrieves the data. Okay, so we'll see what is hashing. Okay, with an example. So here is the hash key, which the data which we want to store, and we give it to the hash function. It generates a hash value, and whatever hash value it generates, that will be used as an index, and that key will be stored in that particular index. Okay, so let's discuss this with an example. Types of hash function. The first one is division method. Okay, so here suppose that we have 54. Okay, we want to store 54, and the size given is 10 here. Okay, so see, we have 10 places here where you can store 54. So what is the formula is, if you have given here 54, do 54 modulus 10. Okay, what do you mean by modulus? Modulus means divided by 10 and take the remainder. 54 divided by 10 is 54 divided by 10. If you take the remainder, you will get as 4. So in the fourth index you'll be storing 54. Okay, got it. Like that, 61 is here. 61 modulus 10 is 1. So in the first index you'll be storing 61. 78 modulus 10 is 8. So in the 8th index we'll be storing 78. Okay, so this is the division method. So the key which you are passing is the value which you need to store, and this is the hash function which calculates the hash value. The answer which you get, this is the hash value. Hash value will be the index. The key is the thing which you want to store here, that will be stored in that particular index. Okay, this is the division method. Second is mid square method. Okay, so for example, the question can be, calculate the hash value for the keys 1 2 3 4 using the mid square method. Okay, so for 1 2 3 4 we have to calculate. This is 1234. Okay, the hash table has 100 memory locations. Okay, so 100 memory locations are there. That means the values can be from 0 to 99. That means 2 digit values can only be there at max. Okay, so k is equal to 1 2 3 4. The key is given 1 2 3 4. It is mid square method, right? So we have to do the square. K square will be 1522756. Okay, so the middle value of this is just 2 here, right? The middle value is 2, but we need the 2 digits here. We have the space for 2 digits, right? So we'll take 2 digits. So the middle value you take and plus 1. Okay, so 27. So in the 27th index you will be storing 1 2 3 4. Okay, this is the mid square method. The next one is folding method. Calculate the hash value for the following. Okay, 5 6 7 8. The folding method, what it does, you will divide this into 2 and add up. When you add up, you will get 134. Then you divide this into 2, 32 and 1, 32 plus 1, 33. Store 321 in 33 index. This divided by 2, divided by 2. 34 plus 56 plus 7 is 97. In 97th index, you'll be storing this number 3, 4, 5, 6, 7. Okay. So these are the three methods used for hashing. Okay, most popular ones. Now, the sometimes what happens, the hash value will come as same. That means same index will come. In that case, we have to resolve it. Okay, collision happens when we obtain the same hash value for two different keys. For example, if 291 is there, if you take the division method, 291 modulus 10 is 1. 291 will store in the first index. Next number we have 31. 31 modulus 10 is also 1, but already 291 is stored in the first index. How can we store 31 on top of that? That is, this is a situation of collision. How do we resolve it? There are few methods for that. Okay, the first one is linear probing. So consider a hash table of size 10. Using linear probing, insert the keys 72, 27, 36, 24, 63, 81, 92 and 101 into the table. Okay, now see, we'll be using the division method only. We'll be doing the modulus 10 for all of these numbers. We'll be getting the remainders here. Based on the remainders, one by one we will be storing it. Okay, first 72, we'll be storing 72 in the second index. Okay, we have stored it. Next 27 will be storing in the 7th index. We have stored 27 here. 36 will be storing in the 6th index. We have stored 36. 24 will be storing in the 4th index. 24 is stored. 63 will be storing in the 3rd index. 3rd index we have stored here. 81 when we get, we will be storing in the 1st index. 81 we have stored in the 1st index. 92 modulus 10 is 2. But in 2nd index already 72 is stored. Now we have a problem. How do we resolve it? See, 92 cannot be stored here because already 72 is there in the 2nd index. So what we do is, we'll move forward and see which is an empty index. See, the circle ones are the one which I have already filled. Okay, so these are the filled ones. 5 is empty, 8 is empty, 9 is empty, and 0 is empty. Okay, this I have filled because this is the final answer. But 92 is here, right? What we will do is we will keep on checking after this one. 2 is filled. That 2 was the index, so 2 is filled. We'll check 3. 3 is also filled. 4 is also filled. 5, when we check, nothing was stored in 5. There is no value stored in 5, right? So we'll store 92 in 5, like that. Whenever a value is already having a value, we'll be checking the next free index and we'll be storing there. Same thing for 101 also. 101 is the index 1. Index 1 is already stored here, so this is also stored. But 8th index is free because nothing 8th index was here, so we'll be storing 101 in 8th index. This is called as the linear probing. Next one is quadratic probing. Here, instead of searching the next empty space like how we did here, after this next empty space we stored 92. Here what we'll do, we'll search plus 1. We'll search here plus 1, whether this is free or not. If that is not free, plus 4 we will search. If that is not free, plus 9 we will search. Like that, okay? Like 1, 2 square, 3 square, like that. That's why it is quadratic probing. Next one is double hashing. Here a second hash function is used to resolve collision. Okay, so here we'll use another hash function which is using this formula m minus key modulus m. Okay, if there is a collision, we'll be applying this formula and finding out the index. Okay, so for example, if these values are present here and m value is given as 7, now we'll do the normal division method. We'll get 7 here, 90 0, 45 5, 22 2, 17 will get as 7. When we get as 7 here, that means already it is stored here. We need to resolve this. To resolve this, the key value we have is 17. We'll apply this formula. H of key is equal to m minus key modulus m. M is 7. So plugging in the values, h of 17 is equal to m value is given as 7. 17 modulus 7, that is 7 minus 2, that is equal to 3. You'll get the value of 3. So in 3, is anything stored? No, it's not stored. So we'll store the value in 3. If 3 also it is stored, then we need to find out another function. Okay, we cannot use double hashing. Okay, in double hashing only 2 times function is used. So in the same way, 49 and 9 is stored. In ninth index 49 is stored. For the 55, fifth index, already fifth index is stored, so we again do the same thing. Key is 55. 7 minus 55 modulus 7. 7 minus 6 is equal to 1. First index, nothing is stored, so we'll store 55 in the first index. So this is how the thing will look like. Okay, this is how the final answer will be. The next method is rehashing. Okay, when the hash table becomes full or nearly full, the hash table size is doubled. Okay, the hash table size double. If it is 10, it will become 20. Okay, and the previous entries needed to be moved to the new hash table with the new hash value. Since the size is increased, we have a greater value. Before we were doing modulus 10, now size is 20. We'll do modulus 20. Okay, so for example, if it was x modulus 5 was the initial hash function, new hash function could be x modulus 10, and all the previous values which are stored, that have to be done with modulus 20 or whatever the double value it is. You have to do that and store in those locations. Okay, the last one is chaining. Construct a hash table for the size 5. The size is given here, and store the following words like a tree, you, first, a, place, 2. Okay, so what is the hash value of like? How do we calculate this? In English alphabets, L is the 12th letter, I is the 9th letter, K is the 11th letter, E is the 5th letter. Add up all of this. What answer you will get? Modulus that size which is given to us. That is the index where you will store like that for all of them you do, and you will find out the values. And we obviously we will be getting the similar values also. So what we'll do is whatever is similar, we'll be putting it on means attaching it. Okay, see, for a we got as 1. For like also, not like, for u also we got as 1. So first we'll insert a here, and after that we'll put an arrow here and we'll put u here, and whatever is the end we'll put as null value here. Okay, so like, first, and place all came as 2, right? Like came as 2, first came as 2, and place also came as 2. So we'll be putting arrows in that same order, like, first, and then place. Okay, now the types of hashing, the static and dynamic hashing. Here in static hashing, the table size remains fixed. Okay, for example, linear probing and chaining, here the size is fixed, that is why it is called as static. Okay, next one is dynamic. Dynamic means the hash table size increases as the collision occurs. Whenever collision occurs, we need to resolve the collision. For that we need extra space, so we'll increase the size. Okay, So here's an example. Okay, see, first four values we are considering here: 0, 0, 0, 1, 1, 0, 1. Okay, 0, 1, 2, 3. Now, A, B, A0, B0, A1, B1, C2, and C3 are stored here. Suppose another one comes as C5. Now, C5 is colliding with 1. Okay, C5 is colliding with 0, 1. So, what we do is we'll increase the size. It was till 1, 1. Now, from 1, 1, we'll make it as 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. Okay, so the for 0, 0, it is coming this one, 0, 1 it is coming this one, 1, 0 it is coming here, and 1, 1 it is coming here. So it was colliding with this one, right? 0, 1 it was colliding with, C5 was colliding with 0, 1. Suppose now we will store, instead of 0, 0, 1, we'll be able to store in 1, 0, 1. The remainder will be same here, but in 1, 0, 1 we'll be storing C5. Okay, like that. And the other ones will be the same one. See, 1, 0, 0 and 0, 0, 0, the ending two digits are same, so the remainders will be same. This can be stored both in here and here, so the pointer is made in both directions. Okay, like that. And C5 will be stored here because already this is full here, A1 and B1. Okay, and we will keep on going like this until the collisions get over or the elements get over. Okay. Second one is dynamic hashing without directory. This one was with directory. Okay, now this is without directory. In without directory, the size of hash table is increased as well as the pages are split. Okay, two things happen. Insert in order the linear hashing 1, 7, 3, 8, 12, 4, 11, 2, and 10. Okay, observe carefully. Now 1, 7, 3, 8, and 12 I insert it normally here. 0, 1, 2 I have the value as modulus 3. Okay, 1 modulus 3 is 1, so I'll be storing it in 1. 7 modulus 3 is 1, 3 modulus 3 is 0, 8 modulus 3 is 2, 12 modulus 3 is 0. Now, when 4 comes, 4 modulus 3 is what? 4 modulus 3 is equal to 1, but 1 is already filled, so we have to add a 4 like this and create a new space for 4. Okay, so see, when we add a 4 here and we create a new space for 4, we use mod 6. Okay, we'll double it. First one we are using mod 3, now we will be using mod 6. Now mod 6 we will be applying for all of these values. Okay, when we do mod 6 for 3, what we'll get? 3 mod 6 is equal to 3, 12 mod 6 is equal to 0, 1 mod 6 is equal to 1, 7 mod 6 is equal to 1, 4 mod 6 is equal to 2, 4 mod 6, sorry, it is 4, and 8 mod 6 is equal to 2. Based on those answers we will be writing here. Okay, see, we have inserted 3 here. Okay, first it was till 2, so I'll make it as 3. When we do 3 mod 6 we'll be getting as 3. Okay, but for 4 still it is here, it is outside, so we need to take another one for 4 here. We'll put it as 4 here, and 4 will be put here. Okay, now we'll continue with the remaining elements till 4 we have inserted. 11, 2, and 10 is remaining, so we'll be inserting 11, 2, and 10. Okay, so how do we insert 11, 2, and 10? First, we'll be doing the same thing. 11 modulus 6. What is 11 modulus 6? 11 modulus 6 will be equal to 5. Okay, um, sorry, now we'll not be doing modulus 6 since we have done the split. Okay, see, when we will be doing with 6 is if a new element comes like this, then only we'll be doing with 6, and when it is resolved we'll be again coming back to 3. Okay, so we have come back to 3 here. When we'll do for the 3, we'll be getting for the 11. What is 11 modulus 3? It is equal to 2, so it will be stored here with 8. Okay, and the next one is 2. 2 modulus 3 is equal to 2, so 2 will be stored here. And the last one, 10. 10 modulus 3 is equal to 1, right? So we'll be storing 10 here. It should be actually 10 here. Okay, so 10 will be present here. Now again we have to accommodate 10 and 2, so we'll be taking it as 5 and again doing modulus 6 and continuing. Okay, so like that it continues till we reach the end of the elements. Okay, so this is how the dynamic hashing without directory is performed. Okay, moving on to the next topic, which is priority queues. There are two types: single and double. Okay, single-ended priority queue, what it is it can be categorized as min or max. Okay, in single-ended priority queue, you have min priority queue and max priority queue. Okay, in double also it is there. So in priority queue, it is having min and max priority queue. Operations supported by min priority queue are: return an element with minimum priority, insert an element with arbitrary priority, delete an element with minimum priority. Okay, same can be said for the max priority also. Instead of minimum, it will be maximum. And here heap data structure is used. For For double-ended priority queue, the priority queue can perform both the operations of min and max simultaneously, so it is called as double-ended priority queue. It can retrieve minimum as well as maximum priority element. Here it can insert arbitrary element, and minimum as well as maximum priority element it can delete. Okay, so that is the difference between single and double-ended priority queue. Next is the leftist tree. In leftist tree, it uses the concept of extended binary tree. So normal binary tree means what? All the elements to the left are smaller and all the elements to the right are greater than the element which are considered. Okay, that is called as normal binary tree. Now, instead of child nodes, you will be making some squares here. If you make a square, that is called as extended binary tree. Okay, now there are two types of leftist trees: the height based leftist tree and the weight based leftist tree. Okay, so here we are finding shortest value, shortest of any node x. Okay, in the tree, if you take any node, that node we are taking as x, and the value of that shortest of that value will be 0 if it is an external node. External node means the last node. This will be 0, this will be 0, this will be 0, and so on. Okay, and else it will be 1 plus minimum of shortest of left plus or shortest of right. Whichever is more shorter, take that and add 1 if it is any other node which is in middle. Okay, means take the shortest from here and the shortest from here, which is more minimum, take that and add 1. Okay, 1 because this node is considered. Like that we will calculate and find out the shortest values. Now, a leftist tree is a binary tree such that if it is not empty, then shortest of left should be greater than or equal to shortest of right. Always the shortest of left should be greater than or equal to shortest of right, then it is called as a leftist tree. Okay, now we can have min leftist tree and max leftist tree. In min leftist tree, we will have a key value for each node smaller than the key value in its children. So the shortest value which we calculate, that should be smaller in the parent and greater in children. That is called as min leftist tree. If it is greater in parent and smaller in children, it is called as max leftist tree. Okay, that's the only difference. Now, there can be insert, delete, and combine operations. How do we do that? For inserting an element, the new element is combined with the existing leftist tree. For deleting, the L child and R child are combined. Okay, see, for example, if I want to delete this element, this and this will be combined and this will be deleted. Okay, so it will become a combined leftist tree. Okay, now how we will see how combine works, because in both these cases combine is happening, right? If it is insertion of element, if a new element is to be inserted, we will insert it like this. It is combining with the already existing tree. If it is deletion, we are combining these two elements and removing this one. So combine, let's understand how it works. Now see, consider the following leftist tree. Here the shortest is 3, right? Because to reach the external node it is 3, and to reach the external node it is 2. So left is more and right is small. This is called as a valid leftist tree. Same is valid here as well. Okay, see here, 1, 2, 3, 4. Here it will be 1, 2, 3, 3. Okay, so in any ways we'll be seeing how do we combine these two. So for the combining, the first step you need to choose the smaller root. Is 2 smaller or 5 smaller? 2 is smaller. Well, if we, after choosing which is smaller, take the right tree of that. Right tree of that is 50 and 80 and combine it with the other tree. 50 and 80 you have to put it in the right tree. How do we do that? See, 50 and 80, when we put it here, it will be coming greater than 8, which is 50, and 80 here. So it will be combined in this spot. At the end it will be combined. Okay, 50, 80. After that, the 2 will be remaining just this much tree, right? So what we will do is, after we have got the combined tree, we'll be combining with 2 also. Okay, this is the 2's tree, and the 5 tree which we have obtained, that will be putting into the right. This is how the combination of the uh, leftist tree works. Okay, height based. Now next is the weight based. Here we consider number of nodes in the subtree rather than the length of the shortest route to the external node. Here we'll not calculate the shortest, but we'll calculate how many nodes are there. Okay, so here if it is an external node, there will be 0 nodes, obviously, because there is no children. It is the last node. If it is any middle node, we will be calculating 1 plus sum of weights of children. Okay, means for example, see here, this one has nothing here, nothing here, so 0 and 0 plus 1. Okay, 0 plus 0, 0 and 0 plus 1, so it will be 1 only. Here also it will be 0 plus 0 plus 1 here, 1 1 for this one, 1 for this one. Now for this one, what will be the value of the weight base? For this it will be 1 plus 1 plus 1 here. See, sum of the weights of the children is 1 plus 1, and the sum itself of is plus 1, so it will be 3 here. Like that will keep on going. So here we got as 3. Now the same thing goes here. F is 1 and C is 2. 1 plus 1, 2. and this will be 3 plus 2 plus 1, which is 6 here. So we have got 6 here. But this is not a WBLT. This is not a leftist tree. Why? Because the value of left should be always greater and this should be always smaller. Right should be smaller. But here in this case both are equal. So this is not a valid leftist tree. This is a valid leftist tree. Here it is 1, here it is 0, here it is 2, it is 1, and here it is 4, and here nothing is there. This is the valid binary weight binary leftist tree. Okay. Here also insert, delete, and combine operations can be performed, which is similar to the height-based leftist tree. Okay. Moving to the last topic, which is the optimal binary search tree. Observe carefully. For the given nodes, there can be multiple binary trees. For example, we have the nodes as 5, 11, and 10. Okay. If 5 is the root node, 11 will come here, and 10 is smaller than 11. 10 will come in the left part of 11. If 11 is the root node, 5 will come here, and 10 will come here. If 11 is the root node and 10 comes before 5, so 10 will come here, and less than 10 is 5. If 5 is the root node, 10 and 11. If 10 is the root node, it is less than 10, this is greater than 10. So based on this, we can form multiple binary trees. In optimal binary search tree, we are finding out which is the most optimal one. What do we mean by optimal one? For calculating, for searching any node. Okay, for example, if I have to search 5, searching 5, I got one comparison here. First comparison, I got 5. For here, if I want to search 5, I'll compare with this, I'll compare with this. 2 times I have to search. For this one, finding out 5, compare with this, compare with this, and compare with this. 3 searches are made. So based on that, I've written how many searches are required for searching that element. Now if we calculate the average, here the average will be 6 by 3, which is 2, 6 by 3, 6 by 3, 6 by 3. For all of this it is 2, but for this one, if I want to search 5, I'll search here and here. If I want to search 11, I'll search here and here. For both of these, it is 2. And if I want to search 10, it is in the first one, so it will be here. So 2 plus 2 is 4, 4 plus 1 is 5. 5 by 3 is less than 2. Okay, 5 by 3 is less than 2. Okay, 6 by 3 is 2. Okay, so 5 by 3 it will be less than 2. So this is the most optimal one, right? So this is the most optimal binary tree. Like that, we have to calculate for larger trees, which is the most optimal one. Now, and also the nodes here, the frequency is one, only one time it is coming as 10 here, but in the real life there can be many tens which can come, right? In that case, we'll also have the frequencies, like 5 appears one time, 10 appears 2 times in the tree, 11 appears 3 times in the tree. So let's take this example and see which is the most optimal binary tree. If 5 come one time, okay, 5 come one time, you have to multiply this with 1. Why? Because I am searching for 5, and one time I am searching, means the first operation I got the 5 here, and 5 also appeared one time only. So 1 into 1 is 1 only. So this is one operation here. And if I want to search 11, for 11 3 times it has come. Okay, so for this searching one time 11, I got two operations, first this one and then this one. So for searching level, two operations were there. So if 11 comes 3 times, it will be 2 time, 2 time, 2 time, right? So 3 time it has come, so it will be 2 2 2. So it will be 2 2 2 means 2 plus 2 plus 2, that is equal to 2 into 3. So how much frequency is coming, multiplied by what is the search value here, that I will be getting how many searches I have done. Okay, so it will be 2 into 3. You got my point, right? I'll again repeat. See, 5 is appearing one time, 10 is appearing two time, 11 is appearing three time in some tree. Okay, here it is appearing one time only. So for searching 5, just one operation is needed. Check if this is 5 or not. For checking 11 in this tree, check if this is 11 or not. Check if this is 11 or not. Two operations are there. If it is 10, check this is 10 or not. Check this is 10 or not. Check this is 10 or not. There are three operations present. So if 5 has appeared one time only, so it is fine. 5, I'll check one time only. Okay, one check is made. If 10 is appearing two times, I'll check if this is 10 or not. I'll check this is 10 or not. I'll check this is 10 or not. Again for the second 10, check this is 10 or not. Check this is 10 or not. Check this is 10 or not. Okay, like that. So three operations are required, and it will happen two times because of two tens. Okay, like that. For 11, two operations are required, but it will happen three times, 2 into 3. So what will be the case is 6 here, and this will be 3 into 2, that will also be 6 here. 1 into 1, that is equal to 1 here. So 1 plus 6 plus 6, it's equal to 13. 13 by 3 is the average time for this tree. Like that, also for this tree it will be different, this tree it will be different, this tree, and for all the trees it will be different. Okay, so if you put some common sense, you'll be easily getting to know that the least times we search this, second least times we search this, and most times we search this, it will be the most optimal tree. Okay, let's take this one. Here 11 has the greatest value, so searching is the least number of times is making more sense, right? 3 is here, so searching it only one time is more better, 3 into 1. And 10, it is appeared two times, so searching 10 lesser times than 5 is making more sense. So searching 10 lesser time than 5 means 10 should come first, then 5 should come. Okay, so 2 into 2, and here it will be 3 into 1. 3 into 1 is 3, 2 into 2 is 4, and 11 into 3 is 1 into 3 is 3. So 3 plus 4 plus 3 is equal to 10. 10 is the least value which we have got here. Okay. And 10, it's not just 10, 10 by 3. Okay, because it will be divided by 3 nodes here. That will be the value. This is the least value among all of this. So as you can observe, if frequency is involved, there will be a different optimal binary tree. Normally there was this optimal binary tree. If there was no frequency, if there is frequency, this is the most optimal binary tree. And it will depend on the frequency which will be the most optimal binary tree. Okay. So this is about the binary tree, optimal search binary tree. In the same way, if there are more number of nodes, we cannot use the manual method. We have to use a formula which is in the dynamic programming. Cost of xy. Xy is nothing but the nodes. This can be x, this can be y, this can be x, this can be y, and so on. Okay. The cost between those two is equal to minimum of cost of x and something plus something and y. This something values is nothing but as we progress will be changing. Okay. But x and y will remain constant. Okay. Plus the frequency of xy, the frequency of x and y appearing together. Okay, that means if I want to find out the frequency of 11 and 5, what is the frequency of 11 and 5? 11's frequency plus 5's frequency, that is equal to 3 plus 1 is equal to 4. So here if x is equal to 11 and y is equal to 5, in that case the w of xy will be equal to 1 plus 3, that is equal to 4. Okay, and the cost will be equal to, based on this formula, means the formula will be substituting it here, and then we'll be proceeding. From 0 to 0 the cost will be 0, 1 to 1 the cost will be 0, 2 to 2 the cost will be 0. Okay, so this is a very lengthy one and more complex one. I think it is not part of the syllabus, but even if it comes in exam, if they ask a theory, just write this much, and try not to means spend more time here. If you understand, it's fine. If you don't, you can skip this topic. Why? Because the calculations are very complicated. Okay, so lot of time will be invested there, so plan accordingly. Okay, so that's all for this video, and if you found this video helpful, please do like and subscribe, and thank you so much for watching. I'll see you in the next one.